The universe is a place of endless mystery, a vast expanse filled with questions that defy even our most advanced understanding. Think about it, we've sent probes to distant planets, built telescopes that peer billions of years into the past, and yet space still holds secrets that leave scientists utterly baffled. What if I told you there are at least 30 colossal questions about the cosmos we still can't answer? From the bizarre nature of dark matter to the unsettling silence in our search for extraterrestrial life, these aren't just small gaps in knowledge, they're gaping chasms in our understanding of reality itself. Picture staring up at the night sky, tracing the faint glow of distant stars, and realizing that everything we see is just a fraction of what's really out there. For every discovery we make, space throws another enigma our way, as if teasing us with glimpses of its true nature. Why does 95% of the universe remain completely invisible to us? What lurks inside black holes beyond the point of no return? And how is it possible that entire galaxies behave in ways that defy the laws of physics as we know them? These aren't just scientific curiosities, they're cosmic puzzles that challenge the very foundation of what we think we know. That's exactly what we're diving into today. This isn't just a list of unanswered questions, it's a journey to the edge of human understanding, a voyage into the great unknown where even our boldest theories start to unravel. Some of these mysteries might haunt you long after this video ends, while others could reshape how you see the universe entirely. So buckle up, because by the time we're done, you'll see the night sky not just as a collection of stars, but as a swirling ocean of unanswered riddles, each one waiting for someone, maybe even you, to uncover its truth. Ready to explore the 30 biggest questions about space that still leave scientists scratching their heads? Let's begin. Our first cosmic mystery is one that haunts every astronomer's dreams: dark matter. Imagine you're in a dark room, reaching out to touch something you can't see, but you know it's there because it keeps knocking objects off the table. That's essentially our relationship with dark matter. We can't see it, we can't touch it, but we know it exists because its gravitational pull is yanking entire galaxies into shapes they shouldn't logically take. Here's the wild part: dark matter makes up roughly 27% of the universe, nearly 5 times more than all the stars, planets, and gas we can actually observe. Think about that. Everything we've ever studied through telescopes, from the tiniest asteroid to the most dazzling nebula, barely scratches the surface of what's really out there. The rest, a ghostly web of invisible matter, weaving through space, bending light, and sculpting the cosmos in ways we're only beginning to understand. Scientists first stumbled onto this mystery decades ago when they noticed galaxies spinning faster than they should. According to physics, the outer stars in a spiral galaxy should be moving slower, like a merry-go-round losing speed at its edges. But instead, they whip around just as fast as the inner stars, as if some unseen hand is holding everything together. That's the gravitational footprint of dark matter. So what is it? The leading theory suggests dark matter could be made up of WIMP, weakly interacting massive particles, hypothetical particles that barely interact with normal matter except through gravity. Experiments deep underground, like those in abandoned mines, are hunting for these elusive particles, shielding detectors from cosmic interference. Meanwhile, the Large Hadron Collider smashes protons together at nearly the speed of light, hoping to create and capture traces of dark matter in the debris. But here's the twist: after decades of searching, we've found nothing definitive, no direct detection, no conclusive signal. Just the growing realization that the universe is playing a cosmic game of hide and seek with us. Could dark matter be something even stranger? Some theorists propose it might not be particles at all, but a flaw in our understanding of gravity itself. Maybe Einstein's equations need rewriting at galactic scales. Either way, this isn't just some abstract puzzle. Dark matter holds galaxies together, shapes the large-scale structure of the universe and might even determine the fate of everything in existence. And yet, it slips through our fingers like smoke. That's the maddening beauty of space. It gives us just enough clues to know we're missing something monumental. If dark matter is the invisible glue holding galaxies together, then dark energy is the mysterious force ripping the universe apart at the seams. Here's what makes it so baffling. Back in the 1990s, astronomers expected the universe's expansion to slow down over time, like a ball rolling uphill after the initial push of the Big Bang. Instead, they discovered the opposite. Galaxies are racing away from each other faster and faster, as if some unseen energy is pressing down on the cosmic accelerator. Dark energy isn't just a small player. It makes up a staggering 68% of the universe, dwarfing even dark matter. Think about that for a second. Nearly 7/10 of everything that exists is this enigmatic force, stretching space itself like an invisible rubber sheet. Unlike dark matter, which tugs on galaxies with gravity, dark energy pushes, creating more space between cosmic structures with every passing moment. So what could it be? Einstein actually stumbled onto a clue a century ago with his cosmological constant, a mathematical fudge factor he added to his equations to keep the universe static. He later called it his greatest blunder when the expanding universe was discovered, but now it turns out he might have been onto something. The cosmological constant could represent the energy of empty space itself, a sort of background hum of the universe that never fades. But there's another wild possibility: quintessence. Unlike the steady cosmological constant, quintessence is a dynamic field that changes over time, like a fifth fundamental force waxing and waning across cosmic history. Some theories suggest it could even eventually reverse, collapsing the universe in a big crunch. Here's the kicker: we have no way to detect dark energy directly. We only see its fingerprints in the way distant supernova dimmer than they should be, or how galaxy clusters drift apart faster than gravity alone would allow. It's as if the universe is playing a prank on us, leaving clues just out of reach. What's truly unsettling is what this means for the far future. If dark energy keeps accelerating expansion, billions of years from now, distant galaxies will vanish beyond an invisible horizon, their light never reaching us again. The night sky, now teeming with stars, could one day go dark, leaving future civilizations with no idea a wider universe ever existed. That's the humbling power of dark energy. It's not just reshaping space, but the very fate of reality itself. And right now, we're left staring into the void, trying to decode a force that might forever remain just beyond our grasp. Could our universe be just one page in an infinite cosmic library? That's the tantalizing question behind the multiverse theory, the idea that ours might be just one of countless universes, each with its own unique laws of physics. It sounds like science fiction, but some of the brightest minds in physics take it seriously, thanks to clues hidden in quantum mechanics and string theory. Take Schrödinger's famous cat, both alive and dead until observed. Quantum mechanics suggests particles exist in multiple states at once until measured, collapsing into one reality. But what if every possible outcome does happen just in separate universes? This many worlds interpretation paints a cosmos where every choice, every random quantum event, spawns new branches of reality. Missed the bus this morning? Somewhere out there, a version of you didn't. String theory pushes this even further. To make the math work, it requires at least 10 dimensions far beyond the 4 we experience. These hidden dimensions might curl up in ways that create bubble universes, each with different physical constants. Imagine a cosmic foam where each bubble has its own rules, one where gravity is stronger, another where stars never form. The kicker: we have zero direct evidence. The multiverse debate splits physicists into two camps: those who see it as a natural extension of current theories, and others who argue it's untestable, more philosophy than science. After all, if other universes are permanently cut off from ours, how could we ever prove they exist? Yet the math keeps pointing there. Tiny temperature fluctuations in the cosmic microwave background. The afterglow of the Big Bang show odd patterns some say could be bruises from collisions with other universes. And if the multiverse is real, it might explain why our universe seems oddly fine-tuned for life. So is it science's next frontier or a dead end? Either way, the multiverse forces us to confront a humbling idea. The cosmos might be far stranger than we ever imagined. From stardust to living cells, how did life first emerge in the cosmos? This isn't just a question about Earth's origins. It's a puzzle that could rewrite our place in the universe. Scientists approach it from two explosive angles. Did life spark here through chemistry alone, or did it hitchhike across space? Let's start with abiogenesis, the idea that life arose from non-living matter right here on Earth. Picture our planet 4 billion years ago, a violent volcanic world bombarded by asteroids. Yet in its tidal pools and hydrothermal vents, simple molecules began linking into chains, forming amino acids, the building blocks of proteins. Experiments like the famous Miller-Urey study show how lightning in Earth's early atmosphere could have brewed these organic ingredients. But here's the catch: going from amino acids to a self-replicating cell is like climbing a mountain blindfolded. We've never recreated that leap in a lab. Enter panspermia, the wild alternative. Instead of life starting here, what if it rained down from space? We've found organic molecules on asteroids, even the sugar that makes up DNA. Some microbes, like the ultra-tough Deinococcus radiodurans, can survive years in the vacuum of space, fueling theories that life could have traveled on comets. The discovery of extremophiles organisms thriving in boiling vents, acidic lakes, or Antarctic ice proves life can endure conditions once thought impossible. If microbes can survive Mars radiation or Europa's icy ocean, why not an interstellar journey? But the plot thickens. Recent missions like OSIRIS-REx are scooping up asteroid samples, hunting for clues. Meanwhile, the James Webb Telescope analyzes exoplanet atmospheres for biosignatures, gases like oxygen or methane that could hint at alien biology. Finding life's fingerprints beyond Earth wouldn't just solve this mystery. It would tell us whether life is a cosmic fluke or a universe-wide inevitability. The answer might lie in both theories. Perhaps the universe seeds worlds with organic building blocks, and local conditions sculpt them into life. Either way, unraveling this riddle doesn't just explain our past, it predicts how common life might be among the stars. Are we truly the only thinking beings in this vast cosmos? The question gnaws at humanity like no other, stretching from ancient philosophers gazing at the stars to modern scientists scanning the heavens with radio telescopes. Consider this: with hundreds of billions of galaxies, each hosting billions of stars and planets, the sheer numbers suggest life should be everywhere. Yet the universe remains eerily quiet, a paradox first crystallized by physicist Enrico Fermi's infamous lunchroom question. Where is everybody? This contradiction, dubbed the Fermi Paradox, gets even stranger when we plug real numbers into the Drake equation. Dreamed up by astronomer Frank Drake in 1961, this formula estimates how many communicative civilizations might exist in our galaxy. Variables range from the rate of star formation to the fraction of planets where life develops intelligence. Optimistic estimates suggest thousands of alien societies could be out there. Pessimistic ones leave us utterly alone. The unsettling truth: after 60 years of searching, we've found zero conclusive signals. Enter SETI, the search for extraterrestrial intelligence, which has turned Earth into one giant ear, listening for cosmic whispers. From the iconic Arecibo dish to today's Allen telescope array, we've scanned millions of frequencies, hunting for patterns in the noise. The WOW signal, a 72-second burst detected in 1977, remains the tantalizing maybe, but despite decades of follow-up, it never repeated. Meanwhile, projects like Breakthrough Listen now analyze petabytes of data using AI, sifting through stellar static for that needle in a haystack transmission. But here's where it gets thrilling. While SETI listens, planet hunters are finding places where life could thrive. The Kepler Space Telescope revealed thousands of exoplanets, including Earth-sized worlds orbiting in their star's habitable zone, the Goldilocks region where liquid water could exist. TRAPPIST-1 rocky planets, or Proxima Centauri b, just 4 light-years away, aren't just dots on a screen, they're potential homes for life. Even more mind-bending, astronomers now detect biosignatures, atmospheric gases like oxygen or methane that could betray alien biology. The James Webb Telescope recently spotted possible dimethyl sulfide in a distant world's atmosphere, a chemical on Earth produced only by life, so why the silence? Theories abound. Maybe civilizations self-destruct before reaching the stars, or they're hiding in stealth mode. Some suggest we're like ants in a rainforest, oblivious to higher dimensional beings all around us. Or perhaps the most chilling answer is the simplest. In 14 billion years, no one else made it this far. The search continues, armed with tools our ancestors couldn't have dreamed of. Every time we point a telescope at an exoplanet or train an AI on radio waves, we're not just hunting for aliens. We're seeking our own place in a universe that either teams with neighbors or leaves us as its sole, fragile voice. Either possibility is equally humbling. Black holes stand as some of the most terrifying and enigmatic objects in the universe, cosmic traps where gravity wins the ultimate battle, crushing matter into oblivion. Picture throwing a rock as high as you can. Normally, it falls back down, but if you could hurl it at escape velocity, it would break free from Earth's pull. Now imagine a place where escape velocity exceeds the speed of light itself. That's a black hole's event horizon, the point of no return where even light surrenders to gravity's grip. Step beyond it, and there's no coming back, no signal you can send, no cry for help, just an irreversible plunge into the unknown. At the heart of this gravitational nightmare lies the singularity, a point of infinite density where the laws of physics as we know them simply break down. General relativity predicts that all matter crushed inside a black hole collapses into this monstrous pinprick of space-time, a place where gravity becomes so intense that space and time twist into meaningless knots. The singularity isn't just an object, it's a mathematical berserker shredding our understanding of reality. But here's where things get even weirder. Black holes aren't entirely black. Thanks to quantum mechanics, they slowly leak energy in the form of Hawking radiation, a faint glow predicted by Stephen Hawking in 1974. Virtual particles, short-lived pairs of matter and antimatter, constantly flicker in and out of existence at the edge of space-time. Normally, they annihilate each other instantly, but near a black hole's event horizon, one particle might get swallowed while the other escapes, stealing a tiny bit of the black hole's mass. Over eons, this process could cause the black hole to evaporate entirely, leaving behind nothing but a whisper of radiation. This leads us to the infamous black hole information paradox. Quantum mechanics insists that information, the fundamental details of particles, can never be truly destroyed. Yet if a black hole evaporates, what happens to all the information about the stars, planets, or astronauts it devoured? Does it vanish forever, violating quantum law, or is it somehow encoded in the Hawking radiation? Scientists remain fiercely divided. Some argue information is scrambled and returned in a form we can't yet decode, while others propose it's funneled into a parallel universe, a cosmic recycling system beyond our comprehension. Recent breakthroughs have brought us closer than ever to unraveling these mysteries. In 2019, the Event Horizon Telescope collaboration stunned the world by capturing the first ever image of a black hole's shadow, a fiery ring marking the boundary where light spirals into the abyss. Then in 2022, they unveiled Sagittarius A, the supermassive black hole at the Milky Way's heart. these images aren't just snapshots, they're laboratories for testing Einstein's theories under extreme conditions. Yet for every answer, black holes offer new riddles. Do they harbor wormholes to other universes, as some equations suggest? Could they be cosmic vaults, locking away secrets of space-time itself? One thing's certain, as long as black holes loom in the cosmos, they'll keep pulling us deeper into their gravitational enigma, one paradox at a time. When two black holes circle each other in a cosmic dance, they don't just collide, they warp the very fabric of space-time itself. The first proof came in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected ripples in reality caused by black holes merging over 1 billion light-years away. These gravitational waves weren't subtle nudges, they carried the energy of 3 suns converted into pure space-time vibrations, confirming Einstein's century-old prediction that massive objects in motion create waves in the universe's underlying structure. The dance begins slowly, with black holes orbiting each other for millions of years, losing energy in the form of gravitational waves. As they spiral closer, their immense gravity distorts nearby stars and gas, creating a chaotic environment where space itself seems to scream. During the final minutes, they whirl around each other hundreds of times per second, reaching nearly half the speed of light before impact. When they finally collide, they don't crash like billiard balls. Instead, their event horizons stretch and merge, forming a single, wobbling black hole that briefly rings like a struck bell before settling into silence. But here's the puzzle scientists call the final parsec problem. In crowded places like galactic centers, black holes should merge often, yet we rarely spot pairs close enough to collide. The math suggests that once 2 black holes get about 3 light-years apart, gravitational waves alone aren't strong enough to close the gap. They'd stall out, trapped in eternal orbit unless something else intervenes. Possible solutions are as wild as the problem itself. Dense star clusters might kick third black holes into the mix, creating gravitational chaos that slingshots a pair together. Or perhaps swirling gas disks around supermassive black holes act like cosmic glue, creating friction that drags them inward. Some theorists even suggest dark matter could play a role, exerting invisible forces to nudge them past the stalemate. Every merger we detect teaches us something new. Some black holes crash at angles, others spin in perfect sync. Each collision a unique fingerprint revealing how these monsters grow. And with upgrades to LIGO and new detectors like the space-based LISA mission coming online, we're on the verge of hearing the universe's hidden chorus of black hole collisions in frequencies we've never tuned into before. What started as a mathematical curiosity is now a whole new way to explore the cosmos, not with light, but with the vibrations of space-time itself. And each ripple carries secrets about how black holes, some of the universe's most secretive objects, find each other in the vast dark. One moment, space is quiet, the next, it screams. Fast radio bursts, or FRB, are among the most explosive mysteries in the cosmos, packing more energy in a millisecond than the sun emits in 3 days. These flashes of radio waves arrive without warning, sometimes as one-off events, other times repeating in cryptic patterns. They're so powerful that even those originating billions of light-years away can overwhelm Earth's radio telescopes, leaving astronomers scrambling to decode their origins. The first FRB was detected in 2007, buried in archival data from Australia's Parkes Observatory. At first, some dismissed it as terrestrial interference, maybe a microwave oven left running in the observatory kitchen. But then more bursts came, each traced to distant galaxies. The real shocker, some repeat, flickering on and off like a cosmic strobe light. FRB 121102, discovered in 2016, has flared up hundreds of times, while others fire once and vanish forever. So what's behind these celestial fireworks? Magnetars, highly magnetized neutron stars, are the leading suspects. Picture a stellar corpse spinning wildly, its magnetic field so intense it could strip the electrons from atoms halfway across the solar system. When these magnetic monsters undergo starquakes or magnetic eruptions, they might unleash FRBs like cosmic lightning. In 2020, astronomers caught a magnetar in our own galaxy emitting an FRB-like burst, lending weight to the theory. But not all FRBs fit neatly into this box. Some exhibit bizarre properties like polarized waves twisted into corkscrew patterns, suggesting they've traveled through incredibly dense magnetic fields. Others arrive with a steady cadence, almost like a heartbeat. Could there be multiple causes, colliding neutron stars, evaporating black holes, or even cosmic strings? Hypothetical defects in space-time have all been proposed. Then there's the provocative fringe idea, artificial origins. Harvard physicists once calculated that a solar-powered transmitter the size of a planet could generate an FRB, fueling speculation about alien beacons. While most scientists dismiss this as unlikely, the sheer unpredictability of FRBs keeps the door cracked open for surprises. New telescopes like CHIME in Canada are now spotting dozens of FRBs monthly, mapping their locations to galaxy clusters and voids. Each detection peels back another layer of the mystery, revealing how these bursts interact with the sparse gas between galaxies. They're not just cosmic oddities. FRBs might be probes illuminating the universe's hidden structures, helping us map the invisible matter woven through space. What started as a data glitch has become one of astronomy's most tantalizing puzzles. Whether they're dying stars crying out or something far stranger, FRBs remind us that the universe still holds phenomena beyond our wildest imagination, flaring up in the dark, daring us to listen. The universe isn't just expanding, it's doing so at a pace that defies expectations, as if some unseen hand keeps turning up the dial. But here's where things get truly bizarre. When scientists try to measure how fast this expansion is happening, they get different answers depending on where they look. This isn't just a rounding error, it's a full-blown crisis in cosmology that's shaking the foundations of modern astrophysics. Take two of our most trusted cosmic yardsticks. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, measured by satellites like Planck with exquisite precision. It paints a picture of a universe expanding at about 67 kilometers per second per megaparsec. But when astronomers use pulsating stars called Cepheids or exploding supernova in nearby galaxies to calculate the same number, they consistently get a faster rate, around 73. That 6-kilometer gap might sound small, but over cosmic distances, it adds up to a discrepancy that can't be brushed aside. What's causing this tension? One possibility is that dark energy, the mysterious force accelerating the expansion, isn't constant as we've assumed. Maybe it's growing stronger over time, like a spring winding tighter. Alternatively, there could be something fundamentally wrong with how we measure cosmic distances. Cepheid stars, for instance, might behave differently in metal-rich versus metal-poor environments, throwing off our calculations in ways we haven't accounted for. Then there's the nuclear option. Perhaps we need new physics altogether. Some theorists propose an undiscovered particle like a lightweight cousin to the neutrino, altering the early universe's expansion in ways standard models don't predict. Others suggest gravity itself operates differently on cosmic scales, modifying Einstein's equations in subtle but consequential ways. The most radical ideas even flirt with multiple bubble universes colliding, where our local patch of space has slightly different properties than the average cosmos. Every new observation deepens the mystery. In 2023, the James Webb Space Telescope aimed its infrared eyes at Cepheid stars, confirming Hubble's faster expansion rate with unprecedented clarity. Meanwhile, gravitational wave detectors now offer a third way to measure cosmic distances by listening to colliding neutron stars, a method that could break the deadlock. This isn't just academic squabbling. The expansion rate sets the universe's clock, determining everything from the age of the cosmos to the fate of galaxies. If our measurements are wrong, it's like discovering your car's speedometer has been off by 20% the whole time. You've misjudged every turn. Whether the solution lies in hidden cosmic ingredients, measurement errors, or revolutionary physics, one thing's certain: the universe is expanding faster than our ability to explain it. What if the Big Bang wasn't the beginning, just another chapter in an infinite cosmic story? The question of what came before it isn't just speculative, it forces us to confront the limits of physics itself. Time as we understand it began with the birth of space-time during the Big Bang, making before a paradox. It's like asking what's north of the North Pole. The framework we rely on breaks down entirely. One provocative idea is the cyclic universe model, where the cosmos undergoes endless cycles of expansion and contraction. Picture a cosmic accordion. Each Big Bang is followed by a big crunch, collapsing the universe back into a hot, dense state before rebounding anew. In this view, our universe might be one in an endless sequence, each inheriting subtle traces from the previous cycle. Some theories even suggest that the dark energy accelerating today's expansion could eventually reverse, pulling everything back together for the next rebirth. Then there's quantum gravity's wild card, the notion that the Big Bang emerged from a quantum fluctuation in a pre-existing void. In the bizarre world of quantum mechanics, particles blink in and out of existence constantly. Apply that to the entire universe, and our cosmos might be one such fluctuation in a grander multiverse. String theory takes this further, proposing collisions between higher dimensional branes, like membranes in 11-dimensional space, as triggers for Big Bang-like events. But perhaps the most radical rethinking comes from loop quantum cosmology, which suggests time itself might be granular, composed of indivisible chunks. In this framework, the Big Bang could have been a big bounce, where a prior universe collapsed to a tiny size before quantum effects halted the crunch, sending it rebounding outward again. Evidence might even linger in the cosmic microwave background, anomalies in the afterglow that carry imprints of a pre-bang universe. The truth is, we're groping in the dark. Without a theory that unifies quantum mechanics and gravity, questions about the before remain speculative. Yet each hypothesis, whether cycles, quantum origins, or bouncing universes, pushes us closer to rewriting the story of reality itself. Whatever the answer, it's clear the Big Bang might not be the ultimate beginning, but a single note in a far grander cosmic symphony. Picture this: a universe where matter and antimatter are perfectly balanced, two cosmic twins born in equal measure from the energy of the Big Bang. When these twins meet, they annihilate each other in bursts of pure energy, leaving nothing behind. By all rights, the universe should have cancelled itself out in a blinding flash, leaving behind an empty void. Yet here we are, surrounded by galaxies, stars, and planets made of matter, with antimatter seemingly vanished without a trace. This isn't just a quirk of physics, it's one of the most baffling mysteries in existence. Why is there more matter than antimatter? Scientists call this imbalance Barrian asymmetry. For every billion antimatter particles created in the early universe, there were 1,000,000,001 matter particles. That razor-thin margin, just one extra particle in a billion, is the only reason anything exists at all. But how did this tiny excess happen? The answer might lie in a phenomenon called CP violation, a subtle crack in the mirror symmetry of the universe. Normally, the laws of physics treat matter and antimatter as perfect mirror images. Flip a particle's charge C for charge conjugation, reverse its spatial orientation P for parity, and it should behave exactly like its antimatter counterpart. But in 1964, researchers studying unstable kaons discovered something shocking. Antimatter particles sometimes decay differently than their matter counterparts. This broken symmetry CP violation could be the key to why matter won out. If antimatter decayed just a fraction more often in the early universe, it could have tipped the scales in matter's favor. Enter CERN, where scientists are recreating the conditions of the infant cosmos to hunt for clues. The LHCb experiment, for instance, smashes protons together and meticulously tracks how beauty quarks, a type of fundamental particle, decay into matter versus antimatter. Recent results show CP violation in these decays, but not nearly enough to explain the universe's staggering matter dominance. The plot thickens when neutrinos enter the picture. These ghostly particles might oscillate between matter and antimatter states differently, adding another layer to the asymmetry puzzle. Could there be undiscovered particles or forces tipping the scales? Theorists speculate about leptogenesis, where heavy neutrinos in the early universe decayed unevenly, producing more matter. Others suggest the imbalance might be written into the fabric of space-time itself, with cosmic inflation amplifying a tiny initial preference for matter. Every experiment brings us closer to solving this existential riddle, because if we can't explain why matter exists at all, we're missing a fundamental chapter in the story of the cosmos, one that literally made our reality possible. Imagine a star so dense a teaspoon of its material would weigh 1 billion tons, then crank its magnetic field up to 1,000,000 billion times Earth's. That's a magnetar. These cosmic powerhouses are neutron stars turned up to 11, where gravity crushes protons and electrons into a sea of degenerate matter so extreme it defies every material science law we know. While all neutron stars are bizarre, magnetars dial the weirdness to levels that make physicists question reality itself. At their core, these objects are thought to be made of neutronium, an exotic state where atoms no longer exist, and matter becomes a superfluid of neutrons packed tighter than nuclei in an atom. But here's where it gets wild. Under such insane pressures, theories suggest some neutrons might break down into a soup of quarks, or even stranger, strange matter that could infect normal matter like a cosmic virus. Probe deeper, and the core might form bizarre quantum condensates where particles pair up in ways that generate the strongest magnetic fields in the universe. Those magnetic fields aren't just strong, they're apocalyptic. A magnetar's field is so intense it can literally twist the star's crust, creating starquakes that release energy equivalent to 100,000 suns in milliseconds. In 2004, a magnetar 50,000 light-years away unleashed a flare so powerful it compressed Earth's magnetic field and ionized our upper atmosphere, all from halfway across the galaxy. Yet for all their fury, we've barely scratched the surface of how these objects work. Recent observations of a magnetar called Swift J1818 01607 revealed it spinning faster than expected, hinting at interior dynamics we can't yet model. Some theories propose tangled magnetic fields inside act like cosmic springs, storing energy until they violently snap. Others suggest magnetars might be born from the rarest stellar collisions, where two neutron stars merge into something even more extreme. What makes these monsters truly humbling is how they push physics to its breaking point. In their cores, matter might exist in states not seen since the first second after the Big Bang, a laboratory for conditions no Earth experiment could ever recreate. Every flare, every pulse is a message from the edge of the known universe, written in the language of twisted space-time and quantum chaos. And until we untangle that code, magnetars will keep reminding us just how much we have yet to learn. Neutron stars are cosmic tightrope walkers, balancing between total collapse and explosive disintegration with nothing but quantum laws keeping them intact. Imagine taking the mass of our Sun and squeezing it into a sphere the size of Manhattan. The result is a neutron star where matter gets compressed so tightly that atoms cease to exist. Electrons are crushed into protons, forming a sea of neutrons packed shoulder to shoulder like sardines in a can. But this extreme density is only half the story. What keeps these stellar remnants from imploding further into black holes or flying apart entirely is a delicate interplay of forces we're still struggling to understand. At the heart of this balancing act is something called the Tolman-Oppenheimer-Volkoff limit, named after the physicists who first calculated it. This cosmic tipping point around 2 to 3 solar masses marks the boundary between a stable neutron star and a black hole. Cross it and gravity wins, crushing the star into oblivion, but hover just below and quantum pressure from neutron degeneracy pushes back, creating an equilibrium that defies common sense. Think of it like a skyscraper held up not by steel beams, but by the sheer refusal of its own particles to occupy the same space. Dive deeper, and the neutron star's interior becomes even stranger. Beneath the solid crust, a crystalline lattice of iron nuclei swimming in a neutron ocean, lies a core so dense that neutrons themselves might break apart. Here, theorists speculate that quark-gluon plasma could form, a state of matter last seen microseconds after the Big Bang, where individual protons and neutrons melt into a soup of free quarks and gluons. It's like taking a Lego castle and reducing it to a puddle of plastic. The fundamental building blocks are there, but all structure vanishes. Some models even suggest strange quarks might emerge, converting the core into an exotic, strange star with properties that could rewrite nuclear physics textbooks. But the real head-scratcher, neutron stars might contain superfluid cores. Despite temperatures reaching millions of degrees, the insane pressure could allow neutrons to pair up and flow without friction, like helium atoms in a lab experiment but at astrophysical scales. This superfluid would rotate independently from the star's crust, potentially explaining why some neutron stars exhibit glitches, sudden speed-ups in their spin, thought to occur when vortices in this quantum fluid unpin and transfer angular momentum outward. Yet for all our theories, neutron stars keep throwing curveballs. Recent observations of massive neutron stars like PSR J0740 plus 6620, nudging the TOV limit, suggest their interiors might be stiffer than predicted, potentially ruling out certain quark matter models. Meanwhile, gravitational wave detectors await the telltale ripples from a neutron-star merger that could reveal how matter behaves at these extremes. What makes these objects so mesmerizing isn't just their defiance of everyday physics, it's that they're cosmic laboratories, testing the laws of nature under conditions we can never replicate on Earth. Every pulse, every glitch is a message in a bottle sent from the edge of what's possible, and decoding it might just reveal secrets about matter itself that we've barely begun to imagine. At the heart of our galaxy lies a sleeping giant, Sagittarius A, a supermassive black hole 4 million times heavier than our Sun. Unlike the violent monsters we see tearing stars apart in distant galaxies, ours is eerily quiet, emitting only faint flickers of X-rays and radio waves. It's as if we're living next to a dormant volcano, one that occasionally rumbles but hasn't erupted in millennia. So why is our cosmic behemoth so subdued while others feast on stellar material with terrifying gusto? The answer might lie in its diet or lack thereof. Black holes like Sagittarius rely on nearby gas and stars for fuel, but our galactic center is surprisingly sparse. Unlike the dense, chaotic cores of active galaxies, the region around Sagittarius is more like a desert oasis with occasional passing clouds. Sometimes a stray gas cloud or star ventures too close, stretching into spaghetti-like strands in a process called tidal disruption. These rare meals trigger brief flares, like the one observed in 2019 when an object named G2, a potential gas cloud wrapped in a stellar disguise, brushed past the black hole's event horizon, sparking an X-ray light show. But the real intrigue comes from the bizarre G objects circling Sagittarius A. These cosmic oddballs look like gas clouds but move like stars, orbiting the black hole in elongated loops that defy simple classification. Some scientists think they're stars shrouded in thick gas masks, their outer layers puffed up by the black hole's tidal forces. Others propose they're the remnants of stellar collisions, Frankenstein monsters stitched together by gravity in this chaotic realm. What's clear is that these G objects are playing a dangerous game. their orbits bring them perilously close to Sagittarius A, where gravitational tides could rip them apart entirely. Watching their fate could reveal how black holes sculpt their neighborhoods, swallowing some objects while flinging others into the galactic void. And then there's the silence. For all its mass, Sagittarius emits less energy than a dying light bulb compared to the blazing quasars seen in other galaxies. Some theories suggest it's in a temporary lull, having gorged itself in the past and now digesting slowly. Others argue our vantage point hides its activity, like seeing a flashlight beam from the side instead of head-on. Every observation peels back another layer. The Event Horizon Telescope's landmark image of Sagittarius in 2022 revealed its shadow, a dark portal ringed by fiery light. Future missions like NASA's upcoming X-ray observatories aim to capture even sharper details, potentially spotting stars orbiting so close they could test Einstein's relativity under extreme conditions. One thing's certain, hidden within Sagittarius A's quiet exterior lies a trove of cosmic secrets waiting for the right moment or the right technology to reveal them. If black holes are cosmic vacuum cleaners, relentlessly sucking everything in, then white holes would be their bizarre opposites, cosmic fire hydrants violently spewing matter and energy out into the universe. The idea stems straight from Einstein's equations of general relativity, which describe spacetime as a flexible fabric that can warp, twist, and even form tunnels. Mathematically, white holes are just as valid as black holes, but while we've detected gravitational waves from colliding black holes and even photographed their silhouettes, white holes remain purely theoretical ghosts in the equations. The concept first emerged when physicists like Carl Schwarzschild and later Martin Kruskal explored solutions to Einstein's field equations. They found that if you could somehow flip a black hole inside out, reversing its inflow to an outflow, you'd get a white hole, a region of spacetime where nothing can enter, only exit. Picture trying to paddle upstream toward a waterfall that's blasting water outward with such force that even light gets repelled. No spaceship could ever approach it. Any matter or radiation it ejects would slam into you like a cosmic tsunami. One tantalizing link between black and white holes lies in Einstein-Rosen bridges, better known as wormholes. These hypothetical tunnels through spacetime could, in theory, connect a black hole's crushing singularity to a white hole's erupting mouth, offering a shortcut between distant cosmic locations or even different universes. But here's the catch: wormholes are notoriously unstable. The moment even a single photon tries to pass through, most models suggest the tunnel would snap shut like a rubber band stretched too far, stranding anything inside. Some theories propose exotic matter with negative energy could prop them open, but we've never found evidence such material exists. So why haven't we spotted a white hole? For one, they'd be spectacularly bright, ejecting energy at unfathomable rates. Some scientists speculate that gamma-ray bursts, the most energetic explosions in the universe, could be white holes blinking into existence, but these events are fleeting and lack the sustained output white holes should theoretically produce. Others argue white holes can't form naturally. They'd require very specific initial conditions, like a collapsing universe rebounding in reverse, a scenario with no observational support. Yet the idea persists because it challenges our understanding of time and causality. If black holes represent the end of spacetime, white holes could symbolize cosmic rebirth, a place where matter isn't destroyed but recycled. Some quantum gravity models even suggest that when black holes evaporate via Hawking radiation, they might transition into white holes at microscopic scales, spitting out information they once consumed. Until we detect one or rule them out entirely, white holes remain a dazzling what if at the frontier of physics. They force us to ask whether the universe plays by symmetrical rules or if some doors, once closed, can never reopen. Either way, their possibility reminds us that reality might be far stranger than our equations can yet describe. The universe might be threaded with invisible cracks, cosmic strings, hypothetical defects in spacetime left over from the earliest moments after the Big Bang. Picture the cosmos cooling from an unfathomably hot, dense state like molten glass solidifying. Just as imperfections form in cooling glass, spacetime itself could have frozen with flaws, one-dimensional filaments thinner than a proton but stretching across the observable universe, carrying unimaginable density. These aren't just theoretical curiosities. They could be the universe's hidden architects, shaping galaxies and possibly even leaving ripples in spacetime loud enough for us to hear. Cosmic strings arise from phase transitions in the infant universe, moments when the fundamental forces split apart. As symmetry broke, much like water molecules rearranging into ice, spacetime might have formed defects where the transition wasn't perfectly smooth. The result, ultra-dense strands of energy with almost no thickness but incredible gravitational influence. A single cosmic string just 6 miles long could weigh as much as Earth, warping spacetime around it like a taut wire distorting a rubber sheet. If one sliced through our solar system, we'd detect its presence not by light but by the way stars behind it appear duplicated, their light bent around the string like a cosmic magnifying glass. The wildest implication, these strings might explain why galaxies cluster in vast filamentary superstructures, the cosmic web we see today. As strings wiggled and snapped in the early universe, their gravitational shockwaves could have nudged matter into the dense regions where galaxies later formed. It's as if the universe's blueprint was drawn in invisible ink with strings as the brushstrokes. Now, here's where it gets even more fascinating. We might be on the verge of detecting them. When cosmic strings vibrate or snap, they should send out bursts of gravitational waves, spacetime ripples distinct from those made by black holes or neutron stars. The Laser Interferometer Gravitational Wave Observatory, or LIGO, could catch these signals if they're strong enough. Imagine listening for the ping of a spacetime crack reverberating across billions of years, a remnant of the universe's birth cries. Yet the hunt is fraught with challenges. Strings could be so sparse that none cross our observable universe, or their gravitational waves might be too faint for current detectors. Some theories even suggest strings decayed long ago, leaving no trace. But if we do find one, it would be like uncovering a fossil from the first trillionth of a second after the Big Bang, a time before atoms, before light, when the very fabric of reality was still knitting itself together. Whether cosmic strings exist or not, their possibility forces us to grapple with profound questions. Are the largest structures in the cosmos seeded by the tiniest defects? Could spacetime itself be littered with scars from its violent birth? Until we know for sure, these hypothetical threads remain one of the most tantalizing what-ifs in modern cosmology. Pulsars are nature's most precise clocks, spinning with such regularity that their radio pulses arrive on Earth with predictability rivaling atomic timekeepers. But every so often, these cosmic metronomes stutter their rotations, suddenly speeding up in events called glitches. These hiccups might last mere seconds, yet they unleash more energy than 1,000,000 nuclear bombs, leaving scientists scrambling to explain how an object with the mass of a sun crammed into a city-sized sphere can behave so unpredictably. One leading theory points to starquakes, violent cracks in the neutron star's ultra-dense crust. Imagine a sphere of iron so compact that a sugar cube-sized chunk would weigh as much as Mount Everest. Now picture that crust under unimaginable strain from the star's insane rotation, sometimes spinning hundreds of times per second. Like a spinning ice skater pulling their arms in, these stars should slow over time as they radiate energy. But when the crust can't take the stress any longer, it might fracture abruptly, causing the entire star to shrink slightly. Conservation of angular momentum then kicks in, just like that ice skater speeding up as they tighten their spin, and the pulsar surges forward in rotation. But starquakes alone can't explain all glitches. Some pulsars exhibit slow glitches where the spin-up happens gradually over weeks or months. This points to another bizarre phenomenon, superfluid vortices lurking in the star's interior. Beneath the solid crust, neutrons might exist in a frictionless quantum state, flowing like a superfluid. When these vortices whirlpools in the neutron soup suddenly unpin from the crust's lattice structure, they transfer angular momentum outward, giving the star's rotation a sudden kick. Think of it like a merry-go-round where the inner platform starts spinning independently, then suddenly locks with the outer edge, making the whole structure lurch forward. Then there are the outliers, pulsars like Vela, which glitch every few years with startling consistency, versus others that remain silent for decades. Data from telescopes like CHIME and Parkes reveal that some glitches come with aftereffects, where the star's spin rate continues to wobble for months, as if the interior is struggling to settle. Others show anti-glitches, mysterious slowdowns that defy conventional explanations. The challenge: neutron star interiors are denser than an atomic nucleus, making their physics impossible to replicate in labs. Gravitational wave detectors might soon catch vibrations from glitches, offering seismic-like probes into these stellar cores. Until then, each glitch remains a cryptic telegram from the universe's most extreme environments, a reminder that even nature's most precise clocks sometimes lose track of time. The universe isn't just expanding, it's hurtling toward an ending we can't yet predict, a cosmic finale shaped by invisible forces we barely understand. Will it fade into icy darkness, collapse back into a scorching singularity, or tear itself apart atom by atom? The answer hinges on dark energy, that enigmatic force accelerating expansion, and whether its grip tightens or falters over billions of years. First, picture the Big Freeze, also known as heat death. In this scenario, dark energy keeps stretching space indefinitely, pushing galaxies apart until the cosmos becomes a vast, desolate graveyard. Stars burn out, black holes evaporate via Hawking radiation, and matter itself decays into subatomic particles drifting endlessly in the void. Temperatures near absolute zero, and the universe reaches maximum entropy, a state where no energy can be extracted, no light shines, and no life remains. It's not a dramatic explosion, but a slow, inexorable sigh, like embers cooling in an infinite fireplace. Now flip the script: the big crunch. If dark energy weakens or reverses, gravity could claw everything back together. Galaxies would merge in a fiery chaos, cosmic microwave background radiation heating up until it cooks planets alive. Space itself contracts, and the universe collapses into a singularity, a mirror image of the Big Bang, perhaps birthing a new cycle. Some theories suggest this could spark an endless loop of universes, expanding and contracting like a cosmic lung. The catch: current observations show acceleration increasing, not slowing, making the crunch a fading hope, unless dark energy has surprises we haven't glimpsed yet. Then there's the most violent option, the Big Rip. If dark energy grows stronger over time, it wouldn't just push galaxies apart, it would shred reality itself. First, galaxy clusters tear away, then individual galaxies. Stars are plucked from their orbits, planets ripped from their suns. In the final moments, atoms are torn apart, nuclei split, and spacetime fractures into meaningless fragments. The universe wouldn't just end, it would unravel like a thread pulled too tight. The wild card: dark energy's nature. If it's Einstein's cosmological constant, unchanging and eternal, the freeze wins. But if it's dynamic, like quintessence, all bets are off. Some models even suggest a big slurp, where a vacuum decay bubble wipes out the cosmos in an instant. For now, we're left watching the universe's acceleration, searching for clues in supernova and galaxy maps. The ending isn't just a question of curiosity, it's a countdown written in the fabric of space itself, ticking toward a destiny we're only beginning to decipher. Some cosmic rays don't just break records, they shatter the very laws of physics as we know them. Take the so-called "oh my God" particle detected in 1991 over Utah. This single subatomic projectile packed the kinetic energy of a baseball traveling at 60 miles per hour, except it was smaller than an atom, screaming through space at nearly the speed of light. The kicker, according to our best models, nothing in the Milky Way should be capable of accelerating particles to such ludicrous energies. So where did it come from, and how did it get here without disintegrating into oblivion? These ultra-high-energy cosmic rays, some carrying over 100 million times more energy than anything our largest particle colliders can produce, shouldn't exist. At such velocities, Einstein's relativity predicts they'd lose energy rapidly as they collide with photons from the cosmic microwave background, the universe's leftover glow from the Big Bang. It's like trying to sprint through a hailstorm. You'd expect to be slowed down. Yet these particles arrive at Earth with barely a scratch, as if they've cheated the universe's speed limits. Possible culprits: active galactic nuclei, where supermassive black holes spew jets of plasma powerful enough to launch particles across cosmic distances. Or perhaps colliding galaxy clusters, where magnetic fields twist into cosmic slingshots. Some theorists even point to gamma-ray bursts or magnetars, those ultramagnetic neutron stars capable of wrenching spacetime itself. But here's the catch: most of these sources lie far beyond our galaxy, and over such vast distances, these particles should have been absorbed or deflected. Unless they're riding some unseen cosmic highway, a network of intergalactic magnetic fields we've yet to map, then there's the truly bizarre possibility these particles might not be protons at all. Some could be heavier atomic nuclei or even exotic dark matter particles interacting with our atmosphere in ways we don't yet understand. Experiments like the Pierre Auger Observatory in Argentina and the telescope array in Utah are now hunting for clues, tracking the faint ultraviolet glow these rays leave as they collide with Earth's atmosphere. Each detection is like finding a single fingerprint at a crime scene, hinting at origins far grander and more violent than we've imagined. What makes these particles so mesmerizing isn't just their defiance of physics, it's that they might be messengers from the most extreme environments in existence. Decoding their secrets could rewrite our understanding of everything from particle acceleration to the large-scale structure of the cosmos. Until then, every "oh my God" moment reminds us that the universe still holds surprises capable of leaving even the brightest scientist speechless. Quasars are the universe's ultimate powerhouses, blazing with the brightness of 1 trillion suns packed into a space no larger than our solar system. At their core lies a supermassive black hole, not passively lurking like Sagittarius in our Milky Way, but voraciously feeding, guzzling down gas, dust, and even entire stars at a rate that defies imagination. The energy released in this cosmic feast doesn't just flicker, it outshines entire galaxies, lighting up the early universe like beacons across billions of light years. But here's the puzzle: how can something known for devouring light become the most luminous object in existence? The secret lies in the chaos just outside the event horizon. As matter spirals toward the black hole, friction heats it to millions of degrees, creating a swirling maelstrom called an accretion disk. This isn't like water circling a drain. It's a frenzied particle accelerator where magnetic fields twist into cosmic tornadoes, launching jets of plasma at nearly light speed. These jets, stretching hundreds of thousands of light years, slam into intergalactic gas, glowing with the fury of 1 billion supernovae. The efficiency is staggering. Up to 40% of the infalling mass converts directly to energy, dwarfing the paltry 1% yield of nuclear fusion that powers stars. Yet the real mystery isn't just the raw power but the endurance. Some quasars have burned brightly for over 10 billion years, far longer than their fuel reserves should allow. One theory suggests they're not just feeding on stray gas but entire galaxies worth of material funneled by cosmic collisions. Imagine 2 galaxies locked in a gravitational dance, their gas clouds stirred into a frenzy, pouring into the central black hole like water into a whirlpool. Others propose that quasars might tap into the black hole's spin itself, harnessing energy from the swirling spacetime around it like a giant dynamo. Then there's the enigma of their golden age, why quasars were thousands of times more common in the early universe. Back then, galaxies were gas-rich and crowded, creating perfect feeding grounds. But as the cosmos expanded, the buffet dwindled, leaving most quasars to fade into obscurity. Today, we only see their faint echoes in the hearts of distant galaxies, where supermassive black holes now slumber. What makes quasars more than just cosmic oddities is their role as universe shapers. Their fierce radiation and jets can blow away star-forming gas, halting the growth of galaxies. They're not just monsters, they're sculptors, carving the large-scale structure of the cosmos with their brilliance. And every flicker we detect, every spectrum of light analyzed brings us closer to understanding how the darkest objects in existence can ignite the brightest fires in the universe. Turn the moon around and you're faced with a cosmic puzzle. Why does its far side look nothing like the familiar face we see from Earth? The near side is dotted with smooth, dark plains, ancient lava flows called Maria, while the far side is rugged, pocked with craters, and sports a crust nearly twice as thick. This stark duality has baffled scientists for decades, and the answer might lie in a cataclysmic collision billions of years ago that reshaped the moon before it even cooled. The leading theory, a giant impact not long after the moon's formation. Picture this, the young moon, still molten from its violent birth, likely from a Mars-sized object slamming into early Earth, is bombarded by a dwarf planet or massive asteroid. This second colossal hit slams into the near side, vaporizing part of the crust and leaving the far side relatively unscathed. The impact would have sent shockwaves through the lunar interior, pushing molten material toward the far side, where it cooled into a thicker crust. Meanwhile, the battered near side remained thin, its wounds later filled by lava seeping up through cracks to form the dark Maria we see today. But there's another twist, the lunar magma ocean. In its earliest days, the moon wasn't just hot. It was likely a global ocean of magma, with heavier minerals like olivine and pyrozine sinking to form the mantle, while lighter feldspar crystals floated to the top, creating a primordial crust. Computer simulations suggest that as this magma ocean cooled, tidal forces from Earth's gravity, locked in the moon's synchronous rotation, could have concentrated radioactive elements like uranium and thorium on the near side. These heat-producing materials would have kept the near side mantle warmer and more active, fueling the volcanic eruptions that painted its surface with dark plains. Here's the kicker, China's Chang'e 4 mission, the first to land on the far side in 2019, discovered that the crust there isn't just thicker, it's also richer in minerals like plagioclase, supporting the magma ocean model. Yet the far side's highlands lack the iron and titanium that stain the near side's Maria, hinting at a fundamental asymmetry baked into the moon's infancy. Why does this matter? The moon's two-faced nature isn't just a curiosity, it's a time capsule preserving clues about how Earth and other rocky planets evolved. Every crater, every mineral deposit tells a story of violence and rebirth, of cosmic accidents that shaped worlds. And as we gear up for new crewed missions to the moon, solving this riddle could reveal not just our satellite's secrets, but the untold history of our entire corner of the cosmos. The night of August 15, 1977, was just another shift for astronomer Jerry Amon as he pored over reams of data from Ohio State University's Big Ear radio telescope. Then, halfway through the printout, he spotted a vertical column of alphanumeric code so extraordinary that he circled it in red ink and scribbled, "Wow." Beside it, giving birth to one of the most enduring mysteries in the search for extraterrestrial intelligence. The signal lasted 72 seconds, blasting at 50 times the noise level of deep space, perfectly matching the narrowband frequency that scientists had predicted an alien transmission might use. What made this signal so tantalizing wasn't just its strength, it was its specificity. The WOW signal appeared at precisely 1420 MHz, a quiet slice of the radio spectrum known as the hydrogen line, where natural cosmic noise is minimal. Hydrogen, the most common element in the universe, makes this frequency a logical choice for interstellar communication, a cosmic hailing frequency. The signal's intensity also rose and fell exactly as expected for a celestial source passing through the telescope's fixed beam, a telltale curve dubbed the lightning bolt pattern. Yet despite decades of follow-up searches, including Eamon's own efforts and later projects using more sensitive arrays like the Very Large Array, the signal never repeated. Not once. This absence fuels fierce debate. Was it a fleeting alien broadcast, a bizarre celestial phenomenon, or something far more mundane? One camp argues for natural explanations. Could it have been a comet's hydrogen cloud reflecting sunlight, as one 2017 study proposed? Critics swiftly countered that comets weren't in the telescope's field of view that night. Others suggest a passing satellite or military transmission, but no records match the signal's unique frequency and drift rate. Then there's the possibility of interstellar scintillation, the cosmic equivalent of a mirage, where distant radio waves bend around interstellar plasma, briefly amplifying a weak signal into something detectable. It's plausible, but why haven't we caught similar events since? The most electrifying theory, of course, is that we intercepted an alien beacon. The signal's narrowband nature and perfect frequency alignment seem engineered, not natural. If so, it might have been a one-time pulse, a lighthouse sweep we happened to catch mid-flash, or a message we lacked the technology to decode. Modern SETI projects like Breakthrough Listen now scan millions of frequencies simultaneously, armed with AI to spot patterns humans might miss. But the WOW signal remains a singular enigma, a tease from the cosmos, daring us to wonder if, just for 72 seconds in 1977, we weren't alone after all. What if everything we see, every galaxy, every atom, is just a slice of a far richer reality? The idea of hidden dimensions isn't science fiction. It's a serious pursuit in physics born from a century-old puzzle. Why is gravity so absurdly weak compared to the other fundamental forces? A magnet can defy Earth's entire gravitational pull to stick to your fridge, yet gravity governs the motion of planets. This bizarre imbalance might hold the key to unlocking dimensions beyond our familiar four. Enter Kaluza-Klein theory, a radical idea from 1919. Theodore Kaluza proposed that if Einstein's equations were rewritten with an extra spatial dimension, electromagnetism and gravity could unite into a single force, like seeing a shadow and realizing it's cast by a higher dimensional object. Imagine ants living on a tightrope, unaware of the vast park around them. To them, a falling leaf might seem to appear from nowhere. Kaluza's extra dimension curled up so tightly, smaller than an atom, that it's invisible to us, much like a garden hose looks one-dimensional from a distance but reveals its circular cross-section up close. Fast forward to modern string theory, where extra dimensions aren't just mathematical quirks but necessities. To make the equations work, strings, the tiny vibrational threads theorized to compose all matter, required 10 or 11 dimensions. Some models suggest these hidden dimensions aren't curled up but vast, with our universe confined to a three-dimensional brain floating within them, like a slice of bread in a cosmic loaf. This brain-world scenario could explain gravity's weakness. While other forces are pinned to our brain, gravity leaks into the bulk of higher dimensions, diluting its strength from our perspective. Here's where it gets wild. If extra dimensions exist, particle colliders like the Large Hadron Collider might produce telltale signatures, microscopic black holes, or gravitons, hypothetical particles carrying gravity escaping into higher dimensions. So far, no luck, but the search isn't over. Some theories propose dimensions aren't tiny but warped, with gravity funneled through them in ways that distort space-time on scales we've yet to probe. The stakes couldn't be higher. If extra dimensions are real, they'd rewrite the rules of reality, offering portals to technologies or realms beyond our current imagination. Until then, they remain the universe's best-kept secret, a whisper of possibilities tucked between the folds of space-time. Time slips through our fingers like sand, always moving forward, never backward. But what if this familiar flow isn't fundamental at all? What if time, as we experience it, is just an illusion, a side effect of deeper cosmic processes? This isn't science fiction. It's a cutting-edge debate in physics that challenges everything we think we know about reality. At the heart of the mystery lies entropy, the tendency of systems to move from order to disorder. The famous arrow of time, the reason we remember the past but not the future, is tied to this irreversible increase in entropy. Think of a shattered glass. It never spontaneously reassembles because that would require entropy to decrease, violating the second law of thermodynamics. But here's the twist. At the microscopic level, the laws of physics are time-symmetric. A video of two colliding particles looks the same whether played forward or backward. So why does time feel so rigidly one-directional in our everyday world? This paradox leads some physicists to argue that time isn't a fundamental feature of the universe but an emergent property, a collective illusion created by the statistical behavior of countless particles. Just like temperature isn't a property of individual atoms but emerges from their average motion, time might be a consequence of complexity rather than a bedrock of reality. Quantum gravity complicates the picture even further. In Einstein's general relativity, time is woven into the flexible fabric of spacetime, but in quantum mechanics, time is treated as an unchanging backdrop. Merging these two frameworks, a holy grail of modern physics, forces us to confront the problem of time. Some approaches, like loop quantum gravity, suggest time itself might be quantized, flowing in discrete chunks rather than a smooth continuum. Others, like the Wheeler-DeWitt equation, imply time vanishes entirely at the most fundamental level, leaving a static block universe where past, present, and future coexist eternally. Then there's the holographic principle, the radical idea that our three-dimensional universe, including time, might be a projection of information encoded on a two-dimensional surface at its boundary. In this view, time could be like the frames of a movie, a sequence generated by deeper, timeless processes. So is time real, or is it a trick of perspective? The answer might reshape not just physics but philosophy itself. If time is emergent, free will and causality could be illusions. If it's fundamental, we're left to wonder why it flows at all. For now, time remains one of the universe's deepest puzzles, a river we're all floating on, still trying to map its source. Most planets, including those in our solar system, orbit their stars in neat, predictable paths, all moving in the same direction as their star's rotation, like runners circling a track in unison. But out in the cosmic wild, astronomers have spotted exoplanets that break this rule, whipping around their stars backward, as if sprinting the wrong way. These rogue worlds, with their so-called retrograde orbits, shouldn't exist under classic planetary formation models, yet there they are, defying expectations and forcing scientists to rewrite the rules of how solar systems evolve. The leading theory, planetary migration gone wild. When planets form, they're born from a swirling disk of gas and dust that rotates in sync with the parent star. Normally, gravity keeps everything orderly, with planets settling into stable, prograde orbits. But occasionally, gravitational tugs from other planets, especially gas giants, can send a world spiraling inward, its orbit warping until it flips entirely. Picture a game of cosmic bumper cars where close encounters slingshot planets into bizarre trajectories. Some models suggest a younger, more chaotic solar system might have had additional planets that were later ejected, leaving behind survivors with wildly tilted or backward orbits as their only legacy. Then there's the stellar flyby scenario, Stars aren't fixed in space, they drift, and sometimes another star passes uncomfortably close. When this happens, its gravity can yank on planets like a mischievous hand swiping through a mobile. In 2021, simulations showed that a nearby star's gravitational nudge could flip an exoplanet's orbit by over 90 degrees in less than 1,000,000 years, a blink in cosmic time. We've even observed rogue stars skirting planetary systems today, hinting that this gravitational havoc might be more common than we thought. But the most violent explanation involves colossal collisions. Early in a solar system's life, planetary embryos, protoplanets the size of Mars or larger, often smash together. A sufficiently off-center impact could spin a planet so fast that tidal forces from its star eventually drag its orbit backward. It's like a poorly thrown football wobbling end over end until gravity corrects its path, except here, the correction leaves the planet orbiting in reverse. The real intrigue lies in the outliers. Take WASP 17b, a hot Jupiter with a confirmed retrograde orbit, or HAT P7b, where the star's equator and the planet's orbit are misaligned by over 180 degrees. These aren't just oddballs, they're clues to the turbulent histories of alien solar systems. Every backward world we find forces us to reconsider how planets are born, how they move, and just how chaotic the universe can be when left to its own devices. What's clear is this: the cosmos has no rule book. For every orderly system like ours, there's another where planets dance to their own rhythm, spinning the wrong way as silent witnesses to the chaos that shaped them. And with every new exoplanet discovery, we're reminded that the universe's creativity far outstrips our imagination. We can only see so far into the cosmos, a sphere of space stretching about 93 billion light-years across, filled with galaxies, stars, and whispers of the Big Bang. But this observable universe, vast as it is, might be just a speck in an unfathomably larger reality. The rest, an estimated 96% of existence, lies permanently beyond our view, hidden behind a veil called the cosmic horizon. Picture standing on a ship in the middle of the ocean. No matter how sharp your telescope, the curve of the Earth hides everything beyond a certain distance. Space works the same way. Because the universe is only 13.8 billion years old, light from regions farther away simply hasn't had time to reach us yet. But here's the twist: the expansion of space is speeding up thanks to dark energy. Distant galaxies are being dragged away faster than their light can chase us, meaning they'll eventually vanish from our view entirely. The observable universe isn't just limited, it's shrinking over time, like an island slowly sinking into an infinite sea. This leads us to cosmic inflation, the theory that the infant universe underwent a brief but stupendous growth spurt, expanding faster than the speed of light. If inflation happened once, could it still be happening elsewhere? Eternal inflation suggests that while our pocket of the cosmos settled into the universe we know, other regions continue ballooning endlessly, birthing new universes with different physical laws. These bubble universes might pop into existence constantly, each sealed off from the others by horizons expanding faster than light can cross them. We'd never see them, never interact, just one among countless islands in a multiverse ocean. Then there's the shape of space itself. If the universe is infinite, as some measurements hint, then beyond our horizon lies more of the same endless galaxies, stars, and planets stretching forever. But if it's curved like a higher dimensional sphere or saddle, venturing far enough might bring you back where you started, like an ant crawling on a globe. The problem: we can't measure this curvature directly because the observable universe appears flat to our instruments, like a tiny patch of Earth feeling level beneath your feet. And what about the 96% we can't see? Most of the universe isn't just far away. It's made of stuff we fundamentally don't understand: dark matter and dark energy. These invisible components shape the cosmos while remaining maddeningly out of reach, like stagehands pulling strings behind a curtain, the haunting truth. We may never know what lies beyond the horizon. The universe could be an infinite fractal, a branching multiverse, or something beyond our wildest metaphors. But that's the thrill of cosmology. Every limit we bump into is just another invitation to imagine further. Saturn wears its storms like cosmic jewelry, but none dazzle or baffle, quite like the hexagon crowning its north pole. This six-sided jet stream, wider than two Earths, spins with geometric precision that defies everything we know about planetary weather. Unlike the chaotic cyclones of Jupiter or the fleeting tempests of Earth, Saturn's hexagon has raged for at least 4 decades, possibly centuries, its razor-sharp angles unchanging as the seasons slowly turn. How does a planet known for its graceful rings produce something so rigidly angular in its turbulent atmosphere? The answer might lie in an exotic dance of fluid dynamics. Here on Earth, hurricanes spiral into familiar curves, shaped by the interplay of rotation, friction, and temperature gradients. But Saturn, a gas giant with no solid surface, obeys different rules. Laboratory experiments using spinning tanks of fluid suggest that when gases or liquids rotate at varying speeds like Saturn's latitudinal wind bands, they can self-organize into polygons. The hexagon could be a standing wave, a sort of atmospheric resonance where faster-moving jets near the pole interact with slower surrounding currents, locking into a stable geometric pattern like vibrations frozen in place. There's another twist: depth. Earth storms are shallow, powered by ocean heat and terrain. Saturn's hexagon, however, might be a towering structure plunging hundreds of kilometers into the planet's interior, anchored by forces we can't yet see. Data from NASA Cassini probe revealed the hexagon extends high into the stratosphere, with temperature differences between its edges and center acting like invisible walls. Some theorists propose that deep-rooted convection, think of a planetary-scale lava lamp, might be funneling energy upward, sustaining this decades-long tempest. Yet the real enigma is persistence. Most planetary storms dissipate as energy scatters, but Saturn's hexagon endures, unfazed by the planet's 30-year seasons. One radical idea suggests it's a kind of atmospheric crystal, with molecular interactions in Saturn's hydrogen-helium soup creating long-range order, much like how snowflakes grow symmetrical arms. Others speculate that the hexagon is a visual echo of deeper magnetic or tidal forces, a surface ripple hiding secrets about the planet's churning core. What makes this storm so mesmerizing isn't just its strangeness, it's a reminder that the universe often sculpts with shapes we've yet to imagine. From Earth's labs to Saturn's clouds, the hexagon challenges us to rethink how beauty and chaos can entwine on scales beyond our own. And until we peer deeper into those golden clouds, it remains one of the solar system's most hypnotic puzzles. Imagine a world without a sunrise, no star to warm its surface, no steady orbit to mark the years, just endless drifting through the interstellar void. These are rogue planets, cosmic nomads untethered from any solar system, roaming the galaxy in perpetual darkness. Unlike Earth or Mars, which thrive in the comforting glow of a parent star, rogue planets were either born alone or violently ejected from their home systems, cast adrift by gravitational chaos. And here's the jaw-dropping part: they might be the most common planets in the universe, lurking in the shadows in numbers that could dwarf the stars themselves. How does a planet end up orphaned? The process is as dramatic as it sounds. Picture a young solar system, its planets still jostling for position like marbles in a spinning bowl. Gas giants, with their immense gravity, can fling smaller worlds outward in a celestial game of pinball. Sometimes, a close encounter between two giants ejects both, one hurled into interstellar space, the other plunged toward the inner system in a cosmic trade-off. Computer simulations suggest this might happen to as many as 1 in every 5 planets during a system's turbulent youth. Other rogue planets could form straight from collapsing clouds of gas and dust, like failed stars too small to ignite but too massive to be mere asteroids. The real shock came when astronomers realized just how many of these drifters might exist. Traditional planet hunting methods rely on spotting the telltale dimming of a star as a planet transits, but rogue planets have no star to betray them. Instead, scientists turn to microlensing, an eerie phenomenon where a rogue planet's gravity bends the light of a distant star as it passes in front, creating a fleeting but detectable brightening. Surveys like OGLE and MOA have revealed microlensing events suggesting there could be 20 rogue planets for every star in the Milky Way. That's trillions of worlds, untethered and unseen, drifting between the stars. Some of these outcasts might not be frozen wastelands. Tidal forces from their ejection or heat from radioactive decay in their cores could keep subsurface oceans liquid for billions of years. Imagine an Earth-like rogue planet, its icy crust hiding a warm sea beneath, hosting microbial life that evolved without sunlight, powered by hydrothermal vents or chemical energy. It's a haunting thought. The galaxy's most common habitable worlds might be the ones we can barely detect, forever shrouded in night. What's next in the hunt for these ghost worlds? Projects like NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will scan the galaxy with unprecedented precision, potentially spotting thousands of rogue planets through microlensing. Each discovery will peel back another layer of this cosmic mystery, revealing just how many orphans the universe has cast adrift, and whether any might carry the spark of life in their eternal dark. Venus should be Earth's twin, both rocky worlds of similar size, born from the same swirling cloud of dust and gas. Yet step onto its surface and you'd be crushed, scorched, and dissolved in seconds under an atmosphere 90 times heavier than ours, with temperatures hot enough to melt lead. How did two planets so alike in their beginnings veer down such catastrophically different paths? The answer lies in a perfect storm of bad luck, runaway chemistry, and a missing ingredient that might just be Earth's greatest protector, plate tectonics. Start with the air you're breathing right now. Earth's atmosphere is a delicate balance of nitrogen and oxygen, with just enough carbon dioxide to trap warmth without cooking us. Venus, though, is a greenhouse gone mad. Its thick cloak of carbon dioxide, a gas that makes up less than 1% of our air but 96% of theirs, traps sunlight so efficiently that surface temperatures soar to 860 degrees Fahrenheit. This didn't happen overnight. Billions of years ago, Venus might have had oceans like ours, but as the young sun grew brighter, those waters began to evaporate. Water vapor, an even more potent greenhouse gas than CO2, accelerated the warming, baking the oceans dry. With no liquid water left to absorb carbon dioxide through processes like Earth's rock weathering, the gas built up unchecked, turning Venus into a pressure cooker. But why didn't Earth follow suit? Here's where plate tectonics enter the story. Earth's crust isn't a static shell, it's a jigsaw of shifting plates that recycle carbon over millennia. When oceanic plates dive beneath continents in a process called subduction, they drag carbon-rich rocks deep underground, locking away CO2 in the mantle. Venus, for reasons we don't fully understand, seems to lack this planetary recycling program. Instead of plates sliding and colliding, its crust might form a rigid, stagnant lid, trapping heat until catastrophic volcanic outbursts resurface the entire planet in one go. These apocalyptic eruptions would have dumped even more CO2 into the air, sealing Venus's fate. Then there's the mystery of Venus's missing magnetic field. Earth's molten iron core churns like a dynamo, generating a protective magnetic shield that deflects the sun's charged particles. Venus, though similar in size, spins agonizingly slow. One day there lasts 243 Earth days, and its core might have cooled into a sluggish, non-magnetic lump. Without that shield, solar wind could have stripped away any lingering water vapor, molecule by molecule, leaving the planet bone dry. Yet the most haunting question isn't just what went wrong, it's whether Venus was always doomed. Some climate models suggest that if Earth had formed just 5% closer to the Sun, it might have suffered the same runaway greenhouse effect. Others point to chance events like the colossal impact that created our moon, which might have given Earth's rotation and tectonics the kick they needed to thrive. Venus, then, isn't just a cautionary tale, it's a mirror showing how fragile the balance of habitability really is. One wrong step and paradise becomes a hellscape. The next time you look up at the evening star, remember that glowing dot isn't just another planet. It's a warning written in acid clouds, a reminder that even twins can grow up worlds apart. Black holes are cosmic vaults, locking away everything that crosses their event horizon. Or so we thought. Stephen Hawking stunned the physics world in 1974 when he revealed these gravitational monsters aren't completely black. They leak this Hawking radiation, a faint glow of particles born from quantum fluctuations at the edge of the abyss, suggests black holes might slowly evaporate over eons. But here's the paradox. If a black hole vanishes, what happens to all the information about the stars, planets, and unlucky astronauts it swallowed? Quantum mechanics insists information can never be destroyed, yet general relativity claims it's irretrievably lost behind the event horizon. This clash, the black hole information paradox, has divided physicists for decades, sparking debates that cut to the heart of reality itself. Enter the firewall hypothesis, one radical attempt to reconcile the math. Picture an astronaut plunging toward a black hole. According to Einstein, they'd feel nothing unusual at the event horizon, just the gentle pull of gravity until tidal forces rip them apart. But quantum mechanics tells a different story. As Hawking radiation emanates from the horizon, it could create an invisible wall of searing energy, a firewall that vaporizes anyone approaching. This firewall isn't made of fire, it's an artifact of quantum entanglement breaking down at the horizon, turning space itself into a deadly barrier. The idea horrified physicists when proposed in 2012, as it meant rewriting Einstein's smooth spacetime continuum into something far more violent. But there's another way out, the holographic principle. Imagine every bit of information falling into a black hole isn't lost but gets smeared across its surface like a cosmic etch-a-sketch. Just as a two-dimensional hologram can encode a 3D image, the event horizon might store all the data about the black hole's interior in a pixelated, two-dimensional form. When Hawking radiation escapes, it could carry away scrambled snippets of this information like smoke signals from a burning library. Over time, as the black hole evaporates, the original information might re-emerge, albeit in a form so chaotic we'd need quantum computers to decode it. Recent breakthroughs hint at progress. In 2019, physicists calculated that Hawking radiation could indeed carry information by accounting for subtle quantum connections between particles. Meanwhile, experiments with analog black holes made of supercooled atoms or lasers simulate event horizons in labs, offering clues about how information might escape. Even string theory weighs in, suggesting black holes are tangled knots of cosmic strings whose vibrations encode data like a celestial hard drive, yet the mystery endures. Does information linger forever at the horizon, or is it blasted into the universe via Hawking radiation? Could space-time itself be an illusion, with reality playing out on some distant, invisible surface? The stakes couldn't be higher. If black holes really erase information, we might need to overhaul quantum theory itself. For now, these cosmic paradoxes remind us that the universe's deepest secrets often hide in the places where our best theories break down. The universe has a way of humbling us at every turn. Just when we think we've unraveled one cosmic secret, a dozen more emerge to take its place. From the ghostly grip of dark matter to the violent whispers of fast radio bursts, these mysteries aren't just gaps in our knowledge, they're invitations to push the boundaries of what we thought possible. Consider how black holes, once dismissed as mathematical oddities, are now laboratories testing the limits of relativity and quantum mechanics. or how the hunt for extraterrestrial intelligence has evolved from scanning radio static to analyzing the atmospheres of distant worlds for chemical fingerprints of life. Each unanswered question is a compass pointing science toward uncharted territory. What makes these enigmas so thrilling isn't just their complexity, it's how they reveal the ingenuity of human curiosity. The WOW signal, lasting just 72 seconds, sparked decades of debate and technological innovation. The moon's lopsided geology forced us to rethink how planetary collisions shape worlds. Even the quiet of Sagittarius A, our galaxy's dormant giant, challenges assumptions about how black holes feed and evolve. Every mystery is a catalyst, driving us to build sharper telescopes, more sensitive detectors, and bolder theories. And the pursuit isn't just about answers, it's about the journey. The multiverse hypothesis forces us to confront the very nature of reality. The search for life beyond Earth holds a mirror to our own place in the cosmos. Even the humble neutrino, flitting through matter like a phantom, reminds us that the universe is far stranger than our senses can perceive. These puzzles aren't roadblocks, they're the scaffolding of discovery, each one a stepping stone to deeper understanding. So stay curious. The next breakthrough might come from a grad student scribbling equations at midnight, a telescope catching a flicker in the dark, or a particle collider unveiling a hidden dimension. The universe isn't just a collection of facts, it's a story still being written, with plot twists we can't yet imagine, and the most exciting chapters. They're waiting for you to turn the page.